So you might remember from yesterday, our topic this week is graph coloring, specifically vertex coloring. And in case you've forgotten the definition, it's up there. So proper coloring is a way of assigning colors to the vertices so that if two vertices are joined with an edge, they have to get different colors, right? Okay, so at the very end of last lecture, I mentioned that it's NP-complete to determine if a graph has a proper coloring with 3 colors, or to determine if the chromatic number is at most 3. We're not going to prove that because, well, I mean, it's actually not terribly difficult, but we're going to prove a slightly easier version of this, where the number of colors is going to be part of the input. Okay, so I want to now define a decision problem. So the following problem is called, okay, so vertex coloring which is a bit of a too long of a name, so I'm just going to call it vertcol. Okay, and so the input is a graph and an integer, right? And the thing you're trying to answer is whether this graph has a proper K coloring. So question, does G have a proper K coloring? So this is a standard sort of, this is kind of a decision problem, right? The answer is either yes or no. Okay, so what I said yesterday was that, you know, even deciding if a graph has a coloring with 3 colors is NP-complete, right? And this is a kind of, well, proving that, so what we're going to prove is that this is NP-complete, right? And that's a sort of weaker version of that problem because, well, here we have the number of colors as part of the input. But in any case, it's interesting to know that this is NP-complete. So vertex coloring is NP-complete. Okay, so we're going to actually prove this. Okay, so like all of these NP-completeness proofs, well, all of the ones we're going to see in this module anyway, it's not true for all such proofs. But yeah, for all the proofs we're going to see, you know, there's one easy part, which is showing that the problem is in NP, right? And this is something, you know, you should not forget to do. I mean, this is a good way to lose marks, right? So first, well, so why is it in NP? Well, because if you just take any proper K coloring of the graph, so if you have a yes instance and you just have a proper coloring, you can just check, is it true that all the, you know, all the edges have different colors on each end? Does it really use K colors? You know, those are questions you can answer pretty easily. So because of proper K coloring is a certificate for a yes instance that can be checked in, well, time big O of the number of edges, right? So in polynomial time, you could just go through every edge and say, do the endpoints have different colors? And that's so that's polynomial time. Okay, so now we want to prove the hard part, which is that it's NP hard. Well, okay, it's hard. Yeah, the hard part is proving it's hard. Okay, so we show it is NP hard. Okay. And remember how these things work, right? So if you want to prove a problem is hard, you have to take a problem you already know is hard and convert it kind of into this problem, right? And then so then if you could solve this one, you could solve another hard one, so this one must be hard, right? And when, you know, converting it, I mean you need to have a polynomial time reduction. So there's various things we already know are hard. I'm not going to go back to SAT or 3-SAT, so don't worry about that. One of the things we said last week, so remember we proved that the clique problem is hard, and then I said also, for free, you get that the problem of finding a stable set of a certain size is hard. So, but perhaps I should recall this definition. So recall, so in case you don't remember what a stable set is, so a stable set is a set of vertices such that if you take any pair of vertices from S, then, so if you take a pair U and V from S, then they don't form an edge, right? So this is a stable set is a set of vertices with no edges inside of them. Okay, and we already proved last week that it's, so we know that it is NP hard to decide if a graph G has a stable set of size M, right? Where you have to be careful here that M and G are both part of the input of the problem. So we want to take this problem, so we take any input for this problem, we want to turn it into a vertex coloring problem. Okay, so let G and M be an instance. Okay, this doesn't look like very good English, right? Okay, I mean the pair kind of G and M are together an instance of this problem. So the stable set problem, and yeah, we want to convert this into a vertex coloring problem. Okay. Are there any questions so far while I switch the boards? Yeah, it's kind of a clever reduction that we're going to do. So, okay, so somebody gave us a graph G and an integer M. Now I'm going to define a new graph. So, oh, maybe actually first I'll say I'm just going to now define, so let n be the number of vertices in the graph G. So here G is this, right? And I can give the vertices names, right? I can just say, so label the vertices so that the vertex set is V1, V2 up to Vn, right? Just give in any way I just give the vertices names V1 up to Vn. Okay. So we define a graph H, or I'll say we construct with vertex set B, so I'll define these things properly in a second, but the vertex set is going to be V union V prime union C, where V is the original vertex set, where, so V prime is going to be, it's going to be a set Z1, Z2, up to Zn. So it's another set of n vertices, and let me see what I called them. So C is going to be C1, C2, up to Cm. And so V, V prime, and C are disjoint. Okay, so that tells you the vertex set of the graph. So maybe I'll kind of keep a picture of it over here. So yeah, so this is, so I haven't told you where the edges go yet, but I'll tell you that in a second. But yeah, so the graph H, you have three sets of vertices. You have V, you have V prime. These are supposed to be the same size. And you have C, where C has size m. Okay, so now, so the edges of, so H contains the following edges. So first of all, okay, sorry. So it contains all edges in E, first of all. So meaning, if I look at the set B, it's exactly, it exactly looks like a copy of G, right? So on the original vertex set, you just copy the same graph you had before. So it contains also all edges, all possible edges within V prime. Okay. Again, all possible edges within C. So in these sets, you have every possible edge. So just imagine you just take every pair in there, you connect them up. So these things form cliques in the graph. You have all possible edges from B to C. So between here and here, you have every guy here is joined to every guy here. And all possible edges from V to V prime, except the edges which go from Vi to Zi for each I. Sorry, up to n. So between here and here, remember, so the number of vertices here is the same as here, right? And I've labeled the vertices, Z1 up to Zn, V1 up to Vn. So I put all the edges from here to here, except, for example, if I have some guy, let's say V3 here, for example, and I look at Z3 here, there's no edge between them, right? And that's the same for every pair which have the same index, right? Okay, so we want to, so now what do we need to prove, right? Okay, first of all, one thing that should be clear is that this construction only took polynomial time, right? So if you're given the graph G, you could easily just put down, n extra vertices, put all the edges. That takes polynomial time. Put down m vertices here. Join these edges. I mean, this reduction took polynomial time, right? And so now the last thing we need to do is prove that we've successfully transformed the stable set problem into a vertex coloring problem. So in other words, we need to show that there's a proper k coloring of H for some specific value of k, which we get to choose, if and only if the original graph G has a stable set of size m. So what I claim is that H has a proper m+1 coloring if and only if G has a stable set of size m. And so in some sense, n+1 is going to be kind of the value of k in the vertex coloring problem. But we're sort of free to choose that. Okay, so I mean, essentially both directions of this are kind of similar. But so yeah, so I think the more interesting direction perhaps is assuming H has a proper coloring, proving that G has a stable set of size m. So suppose that so suppose we have a proper coloring of H. So remember, this is the vertex set of H. So we're mapping vertices to colors. Well, the colors are just called 1 up to n+1. And vertices joined with an edge get different colors, right? Okay, so, well, remember, so the vertices, so what we want to do now is show that there's a stable set in G of size M. Okay, so the vertices of V prime are a clique. Clique means they're, all joined with edges of size n in H, right? This is just by construction. So therefore, they have to all get distinct colors, because if two of them got the same color, they're definitely adjacent, or there's an edge between them, so that would violate the property. Yeah? Yeah, so we're assuming, so we're going this direction from the first statement to the second. So we're assuming it has the proper, H has a proper coloring. So H is this graph we constructed where we kind of put these blobs around, right? We have V, V prime, and C. And now we're trying to find, so an independent set of size M inside of G, which is like conveniently embedded in H, right? So that's how we're going to find it. Okay, so these, the vertices of V prime are a clique of size N. So therefore, they have to get different colors. So, and we can kind of, so without loss of generality, because we can always rename the colors however we want, right? We can kind of permute the different labels of colors. Without loss of generality, we can assume that f of zi equals I for I from 1 to n. Right? You have a clique of size n, they all get different colors. We might as well assume those colors are the numbers 1 up to n, right? But now, well, let's look at the vertices of G, or V, let's say. So remember how we define these edges, right? So if I look at the vertex VI and look at who it's, who it sends, who it has edges to in V prime, it has an edge going to every single vertex of V prime except for the one which has the same index, right? So, and we know what color the guys in V prime have. So therefore, VI is adjacent. So VI being any vertex, so any VI in V, adjacent meaning joined with an edge, to vertices of every single color except, so I and n plus 1. Okay, so vertices in C prime, right? Yeah. Oh, sorry, V prime, yeah, thanks. Yeah. So if I just look at VI and I look at who it joins to in C, or V prime, it already sees every color there except for its own color and color n plus 1, right? Was there a question? Or so now let S be the set of all VI such that, well, okay, so it's already adjacent to all of these colors. So actually let me say, so therefore, so it's the color of that vertex must be in, it's either I or it's n plus 1. Right, so now we let S be the set of all VI in V such that f of VI equals n plus 1, right? And I claim this is going to be a stable set of size M. Okay, so S is a stable set because F is proper, right? So proper coloring always gives, these guys all get the same color. They all get color n plus 1, so there's no way that two of them could have an edge between them. And why does it have size M? Well, it has to do with this set C, right? We haven't used the set C yet, right? So there are M colors which are used on C, right? And this is again because C is a clique, so all the vertices get different colors, and none of those colors can be used on V. Right? Because if you look at the construction again, everybody in V has an edge going to everybody in C. So if any color gets used on C, then it can't appear anywhere on V, because then you'd have an edge that gets the same color on both ends. Okay. Well, so therefore, so the point now is that, so what, right, so how to say this? Well, one thing is that the color n+1 certainly can't appear on C, right? Because, but is this the most elegant way of doing this? Let's see. Hold on. Okay. Well, so if those M colors, so if the M colors used on C are in 1 up to N, right? Then, so then the corresponding vertices in V, so when I was to say corresponding vertices, right? So each color here is a number between 1 and N. There's a corresponding vertex, right? So I mean, so if you take color I, then VI is the corresponding vertex, right? Must have color n+1, and that would imply that the size of S is at least M, right? Because there's these M colors, all of the vertices, nobody on V can use those colors, so because we know that these vertices in V only use either their corresponding color or n+1, there would have to be at least M using color n+1, right? And this S is exactly the set of vertices using color n+1. Good, we have time. Okay. Well, it turns out that, oops, every time. Okay. Anyway, I'll sort this out in a second. Well, actually, okay. Right, so if color n+1 appears on C, meaning there's some vertex in C which is mapped, which is sent to color n+1, well, then every VI in V must have f of VI equal to I, right? Because we already knew that all of those vertices had color either I or n+1, and if somebody in C uses n+1, then that blocks the color n+1 from all the vertices of V, because every vertex in C is joined to every vertex in V. But then, if M is at least 2, which we can assume here because it's trivial to find a stable set of size 1, right? So we might as well assume M is at least 2. Then there's no way to color the rest, the other vertices in C, because they will see, because they are adjacent, to vertices of every color. Right? Because inside of C, there would be a vertex of color n+1. C is a clique, so they're all joined to that one. And they would be joined to everything they're joined to everything in G, or in V, so they'd see all the other colors over there. Right? So this would be a contradiction. So this can't happen. So what we've proven is that if there is a proper n+1 coloring of H, then G does have a stable set of size M. Right? Now to go the other direction, so the other direction is kind of easy. You sort of just reverse this proof in some sense. So suppose G has a stable set S of size M. Well, yeah. No. So the thing is with the M, you're not allowed to choose it at all in some sense because we're trying to show that the stable set problem. So in the stable set problem, you have an input which is a graph and an integer M, and we have to just take that input no matter what it is, and we have to transform it into the graph coloring problem.
Yeah.
I mean, okay. Technically, we could have reduced the stable set problem for when M is at least 2 to the stable set problem when M is 1, for example, when M can be any integer. Yeah, don't worry too much about the value of M. It's not. I mean, G has a stable set of size. So if M is 1, we're saying, does G have a stable set of size 1? The answer is always yes, right? Because that's kind of a trivial question. So we should always think of M being at least 2. Okay, so yeah, so suppose now it has a stable set of size M. Well, without loss of generality, we can assume that this is just the first M vertices. So it's just V1 up to Vm. Because otherwise, we can just rename the vertices in another way, right? And now we just define function f from V union V prime union C to 1 up to n plus 1 by f of, well, so on the vertices of V, we set f of Vi equal to I if I is in n plus 2 up to, n plus 1 up to n plus 1 otherwise. And so in some sense, we're just going to, yeah, it's not too hard to just construct this coloring, right? We just take, so now f of Zi, we just set it equal to I for all Zi and V prime. And f of Ci, we also let this be equal to I. So, okay, and you can check that this is a proper coloring, and it uses n plus 1 colors, and that completes that proof. Okay, so that's, yeah. So I went through that last bit a bit fast, but yeah. But it's sort of just the same idea as the other proof, but in reverse, right? Okay, so now let's, I just want to prove one quite easy thing, and then that'll be all for today. Yeah, so what we've proven here is that generally it's hard to cover color graph. Yeah? No, because they get used on C. Yeah. Yeah, it's kind of annoying how I've had to kind of break this up into 3 different definitions, but hopefully. Okay, so yeah, so what we've proved is generally it's hard to determine if a graph can be colored with a certain number of colors. Turns out, okay, so if you have a lot of colors, obviously it's kind of easier, right? What do we mean by a lot of colors? So let me give you a couple of definitions first. So I think I've probably defined this before at some point, but let me just recall it in case I forgot to define it. So for a vertex, the degree of V is the number of edges containing V, and we denote this by, so I'll just write it deg of V. And what's going to be important for us is to understand, so what is the biggest degree in the graph? So delta of G is defined to be the maximum degree, so degree of V, such that, yeah, over all the vertices of the graph. This is not going to, so another thing is we can also define the minimum degree. So it's not going to come up in this lecture, but it's useful to have this notation. So capital delta is the maximum degree, little delta is the minimum degree. Okay. Now I'm going to give you a simple algorithm which can properly color a graph as long as the number of colors is bigger than the maximum degree. So this is something called the first fit algorithm, or sometimes called the greedy algorithm. So you just simply order the vertices. Okay, so here I'm going to assume, so the number of vertices is n. So we just order the vertices v1 up to vn in a sort of arbitrary way. And so one by one, so for I starting at 1, and then 2, and then 3, up to n, let f of vi be the minimum, let's say, so C, so the minimum color, so C is going to be the set of colors, or sorry, C is a color, so it's an integer, such that f of vj is not equal to C for all j less than b, or sorry, j less than I, such that vi and bj is an edge. In other words, you just start with the first vertex, you give it color 1, you look at the second vertex, right? So v1 always gets color 1. You look at the second vertex. If it's not adjacent to the first one, you give it color 1. You look at the next vertex. If it's adjacent to one of these previous vertices, I can't give it color 1, but I just give it the smallest possible color that I can give it, which in this case would be 2. Here maybe I have a vertex joined to this guy. I can give him color 1, right? Because he's joined to a 2 but not to a 1, and so on and so forth. So this guy might be joined to both of these. He gets color 3, and so on. This is a really simple algorithm, really easy to implement. And is the algorithm clear, or are there any questions? Actually, I haven't really phrased this as an algorithm, right? I've just written let f of I be this, right? But it's clear how you would kind of, by this example, it's clear how you would algorithmically kind of define the color of each vertex, right? You go through them one by one, and you give it the smallest possible color. Okay, so basically, this is a rather kind of easy theorem, which is going to come just from this algorithm. So the chromatic number of a graph is at most the maximum degree plus 1. Remember, chromatic number is the minimum number of colors that you can use in a proper coloring, right? So the proof is just that, well, so the first fit, so I think it should be pretty clear that the first fit algorithm definitely gives you a proper coloring, right? So because every time if it didn't give you a proper coloring, you should look at the first vertex, which, for which the proper coloring thing was violated. Why was it violated? Well, it got a color that appeared on a vertex that came previously, but that's not what the first fit algorithm does, right? Or sorry, a neighbor of it that came previously. But the first fit algorithm is designed literally to avoid that. So it should be clear that it always gives a proper coloring, and I claim that it uses colors from the set 1 up to delta of g plus 1. Okay? I don't claim that it uses all of the colors, but certainly the colors it uses is a subset of this. Okay? So if not, right? So if not, we can just look at the first time it uses a color outside of this set. So let vi be the first vertex such that f of vi is, let's say, I'll call it C, and this is at least delta G plus 2. Right, the first time that the color went above the max degree plus 2. which, I mean, of course, if it happens at some point, there has to be a first time. Well, why did the color go above the maximum degree plus 2, right? I mean, you always give the vertex the smallest color that you possibly can. So that means that kind of all of the colors below delta of G plus 2 must have been already appearing on the vertices adjacent to that vertex. So VI must have, well, let me just do this more properly. So for every, let's say, C prime between 1 and delta plus, or let's say C minus 1, VI must have a neighbor. So when I say neighbor, I mean that VI, or it's a vertex which has an edge to VI, Vj, with f of Vj equals C prime, and j is less than I. Right? But then this gives you, so, I mean, all of these vertices have to be, these Vj's have to be distinct, so therefore Vi has at least C minus 1, which is at least delta of G plus 1 neighbors. Again, neighbor means a vertex that's joined with an edge to Vi, but that's a contradiction by definition of delta of G. So that you can't have more than the maximum number of neighbors. So that's the end of the proof. Okay, so that's yeah. Well, that's the end of the lecture today.